So today we start section 8.1, and chapter 8 is all about hypothesis testing. So a lot like chapter 7, where we had one topic, confidence intervals, and then we had different situations that all related to confidence intervals. Chapter 8 is just like that for hypothesis testing. So most of the information is in 8.1. And then we make small changes for 8.2 and 8.3, just like we did for chapter 7. So this will be the largest section out of the chapter. So to get started, we've got recall from chapter 7. We use statistical inference to estimate the value or location of a population parameter, and we use mu or p. So now in chapter 8, we're going to use statistical inference again, but this time to make decisions concerning the value of the population parameter. And this is done using hypothesis testing. So first we establish a working hypothesis about the population parameter in question. This hypothesis is called the null hypothesis, denoted by H naught. It looks like H with a subscript 0. And this is the thing we're assuming to be true. So the value specified in the null hypothesis is often a historical value, a claim, or a product specification. And any hypothesis that differs from the null hypothesis is an alternate hypothesis, or sometimes called an alternative hypothesis, denoted H sub 1. And so our book uses this H sub 1. Sometimes you'll also see H sub A. And some of you who have taken stats before have probably used that notation, and that's probably almost as common as this. So if you want to use this, that's fine too. H with a subscript A. And an alternate hypothesis is constructed in such a way that it is the one to be accepted when the null hypothesis must be rejected. So for example 1, we're going to be testing the mean. So we've got this example. It says, suppose a cigarette company claims that the mean nicotine content of a cigarette is equal to 1.5 milligrams. A researcher is skeptical of this claim and believes that the mean will exceed 1.5 milligrams. To test the company's claim, the researcher will test the hypothesis that the mean is equal to 1.5 milligrams. So first question is, what is the null hypothesis? So the way we use this, the notation here is this. We say, typically write something like this, H naught with a colon. Whatever follows that colon is a null hypothesis. That could be an English statement or a sentence, or it could be something like we'll do here. We're just going to say the null hypothesis is the population mean equals 1.5 milligrams. So when we have the null hypothesis, this is the notation that we want. H naught with a colon, and then whatever follows is the thing we're assuming to be true. Right? We have reason at this point to believe this is true. The mean equals 1.5 milligrams. Then the alternate hypothesis, the way we write that is we write H sub 1. Or if you prefer, H sub A, right? That's the other way to write it. And we look at this. So this researcher believes the mean will exceed 1.5 milligrams. So the belief is that the mean is greater than 1.5 milligrams. So the alternate hypothesis is set up this way. Mu is greater than 1.5 milligrams. So when we're testing the mean, these numbers will be the same. And we're going to have, for the null hypothesis, thing we're assuming to be true, the mean equals this. And the alternate hypothesis in this case is the mean is greater than that. So generally speaking, the null hypothesis will look just like this when we're testing the mean. And for us, this will always always be an equal sign here. For the null hypothesis, always an equal sign. That's true for our class always, but it's true in most cases, generally speaking. So there are some exceptions, but most of the time the null hypothesis will be, when you're testing the mean, will be the mean mu equals some number. So for us, it's always going to be an equal sign here for the null hypothesis. And the null hypothesis makes a statement about a population parameter. The population parameter in this case is mu, right? This is population parameter mu. So we're making a statement about population parameter mu in this case. So in other sections, we'll make the null hypothesis will make a statement about a population parameter, which will be P, the population proportion. But right now in this section, we're dealing with the population mean mu. So we've got the null hypothesis, which will look like this. Then there's the alternate hypothesis. And there's 3 different types of these, but we will just use one. So each problem will have a null hypothesis and one alternate hypothesis. So each one of these, there's 3 types, but we will use just one at a time. We'll use one of these. And which one we use will depend on the data. So with judgment, when you pick one of these here, judgment will inform whether we're using this one, or this one. We look at the data. What do the data seem to suggest? And the book will always give us, our book will basically tell us which one of these to use. Now this one, when you have this one, when this is your alternate hypothesis, it just means that you believe mu is less than the value stated in H naught. So for some reason, you just have a belief that the population mean is actually less than that value stated up here. Then you would use this. This is called the left-tailed test, and that reason will make sense later when we see how we calculate this. We're going to use the standard normal curve, and we're going to be in the left tail of it. We're going to find the area under the left, in the left tail of the curve. So it's a left-tailed test. And you can also see this little memory hook. It looks like an arrowhead pointing to the left. So if instead the data that you're looking at seem to suggest that the actual mean is bigger than this number, you would use this one, which is a right-tailed test. And the vast majority of times we use one of these. But you could also sometimes use what's called a two-tailed test. And this is when we'll be looking for area under the curve on both ends of the standard normal curve. So it's a two-tailed test. This is when we say, we're not sure if it's greater or less than this stated value, but we just don't think it's the same as that stated value. So this one's not used as often, but this is when we have null hypothesis mu is not equal to k, which is a two-tailed test. So for hypothesis testing, we take a simple random sample and compute a sample test statistic. And a test statistic is just, finding x bar or p hat. So in this section, we'll be finding x bar. But the sample test statistic corresponding to the population parameter in H naught. And based on the sampling distribution of the sample statistic, we can assess how compatible the sample test statistic is with H naught. So let's take a look at this example 2. So suppose you are working on a CNC machine, computer numerical control. These used to be really popular in the Grand Rapids area when you did a lot of manufacturing. Not as popular anymore. But it would have been, 20, 25, 30 years ago. A lot of you guys during summertime would have worked on CNC machines for summer jobs. College students used to do that quite a bit for a lot of the manufacturing places that were around town. Not very common anymore, but some of you, I'm sure, have worked on a CNC machine. So for this example, we suppose we are working on one of these machines producing pistons. The diameter of the piston is supposed to be 7.00 centimeters. You select a random sample of 20 pistons. So you take this random sample, you've got 20 pistons, and find that the mean diameter of the sample is 6.95 centimeters. Does this mean your machine is not producing pistons with a mean diameter of 7.00 centimeters? So the idea is, as you use a CNC machine, every time the machine goes through a cycle, it has blades on the machine that are getting dull. Every time it cuts apart, the blades become a little more dull, so there's randomness built in. Plus the parts are a tiny bit different, so that if you were to take a couple parts off the line and measure them with a micrometer, there'd be little variations in each part. So we don't expect every part to be exactly the same, right? There has to be a certain tolerance that's met, but we expect them to vary somewhat. So here's the case that we're talking about. Let's say we've got this population. Just think of this as being, we believe that the mean 7.00 centimeters. This is the claim. And just think of this population of having just thousands of numbers in it, thousands of numbers. Each number represents the diameter of a piston. We take a sample out of here. We take a sample of size 20. We sample 20 of them, and we get a mean of our sample is 6.95 centimeters. So would we, after you take this sample, would you say, oh, wait a minute, this can't be true? Or would you think, well, I mean, there's going to be some variation here, right? So maybe you wouldn't think that. So let's say this isn't the one, though. Let's say instead of this, let's say you take a sample, and you take a sample of 20, and your sample is 6.65 centimeters. Okay, what about this? Is this far enough away where you're going to be like, wait a minute, I'm starting to think maybe this claim isn't true. So the question is, how far away from 7 centimeters do you have to get with a sample of 20 before you say, wait, we better take a look here. We better shut this machine down and take a closer look at this. So that's the question. So when we look at this, we look at our sample and we say something like this. When we look at this, is the mean less than 7.00 centimeters? Is it less than that? Well, to answer this question, I'll write this over here. We're getting a little messy here, but to answer this right here, this question, we need to know the probability of getting this sample if this really is true. That's what we're going to look at. To answer this question, is the population mean actually less than 7.00 centimeters? To answer that question, we need to figure out how likely are we to get this sample if this is really true. And we can do that. We can use Chapter 6 information to figure out the probability of getting this sample if this is really true. And if that probability is really low, then we'll be likely to say, you know what, I don't believe this is true anymore. So to answer the question, we need to know the probability of getting X bar equals 6.65 centimeters when n equals 20 and the population mean equals 7.00 centimeters. So that's what we'll do. We're going to take a look at a sample, and we're going to take a look at this claim, and we're going to say, well, assuming this is true, assuming this claim is true, how likely are we to get this sample? And if this is really unlikely, then we're going to be more apt to say something like, you know what, I'm going to reject this. I don't believe this is true anymore. So to get started here with our null hypothesis, it would be the mean equals 7.00 centimeters. And looking at our sample, because this, both of these examples were below 7. So with that in mind, we would probably say we believe maybe the alternate hypothesis is that the mean is less than 7.00 centimeters. So that's kind of what chapter 8 is about. So we have this claim. We want to see how likely that is to be true. So to do that, we take a sample out of this population, like one of these, and then we look at our sample, we look at the mean from the sample and say, well, how likely is it to get this sample if this is really true? In other words, what's the probability of getting this sample if this is really true? And we're just going to use chapter 6 to do that. So with that in mind, let's see. We've got a little box here. And of course, the formatting is off, but yours will look better, I hope. So there's a couple of givens here. And one of these is going to look very similar to chapter 7. So we are given that the X distribution is normal and also that sigma is known. You remember that was just like section 7.1. Chapter 8 is very much like a repeat of chapter 7 with a different idea. We're using a hypothesis test. But our first section, we're starting off assuming that we know sigma, but we don't know mu, which is not all that common. So just like 7.1, we're starting off. We are sampling from a normal distribution, and we know sigma. So we have a test statistic. And this test statistic, this is from the chapter 6 handout. But things we need to know this time is that mu, that will be stated in H naught. So that'll be stated in H naught. Little n, of course, that is the sample size. Sigma will be known at this point in 7.1. 7.2, in 8.1. In 8.2, it won't be known, just like in 7.2. And then this X bar, this is going to be the mean of our sample. So this will be the mean of a simple random sample. And then the test statistic is just going to be a z-score. So basically we're finding the z-score of our test statistic. That's what we've got right here. And then there's a little note here, and we've seen this in the past. Since the X distribution is normal, the X bar distribution is normal also. Right? We learned that in chapter 6. So if we didn't know this, then we'd have to have a sample size of 30 or more, right? So that's just like before. So we've got an example here, which is page 450, number 12. Can you guys believe we're on page 450 already? We're flying through here. Page 450, number 12, we've got A, B, C, and D. Make a little room here. So what you should do is try this out. Press pause, try it out, and then come on back. And hopefully we'll see this. Number 12 says, suppose you want to test the claim that a population mean equals 30. State the null hypothesis. Well, the null hypothesis will look like this. H naught, the mean equals 30. I'm going to tell you what not to do. Don't do this. Some people do this. I don't even know what that means. H naught equals 30. Don't do that. Don't do that. When I'm grading tests and I see that, oh, it's very bad. Gives me bruises on my forehead. Don't ever do that on a test. So the null hypothesis, the notation that's understood everywhere is this, H naught colon, and then this is a statement that follows, right? We're saying, when you see this notation, we're saying what follows is our null hypothesis, the thing we're assuming to be true, mu equals 30. This doesn't make any sense at all. So don't do that. I'm going to write it like this. Then we've got part B, which says, state the alternate hypothesis if you have no information regarding how the population mean might differ from 30. So this one, it's an alternate hypothesis, so it's going to be H sub 1, or if you prefer H sub A, and we're basically saying the mean is not equal to 30. It just says it might differ from 30. So when you see different from, differs from, anything like that, it's a not equals to. Again, this is the one that's not all that common. Greater than or less than are far more common, but that's how you do the differs from, or is not equal to. Okay, part C says you believe, based on experience or past studies, that the population mean may be greater than 30. H sub 1, the mean is greater than 30. And then finally, part D, you believe, based on experience or past studies, the population mean may not be as large as 30. Not as large means that it's less than 30. So sometimes the wording, you have to kind of work through what they're saying. But one thing to notice, H sub 1, H sub 1, H sub 1, these are all alternate hypotheses, and this is the null hypothesis. So example 4, it says the management of a local health club claims that its members lose an average of 10 pounds. Average of 10 pounds within the first month after joining the club. The consumer agency is skeptical of this claim and believes that members lose less than this amount. They took a random sample of 36 members, and I'm just making notes on things that may be important. They found that they had lost an average of 9.2 pounds within the first month of membership. The population follows a normal distribution with population standard deviation equal to 2.4 pounds. So remember, in 8.1, just like 7.1, we know sigma. So it says state the null and alternate hypotheses. Well, the null hypothesis, this thing that we are assuming to be true, well, the claim is that members lose an average of 10 pounds. So average equals 10 pounds, right? That's the claim. That's the claim. That's the null hypothesis. Then we have the alternate hypothesis. And according to this consumer agency, they took a random sample and found the average was 9.2 pounds. So the claim, the alternate hypothesis, is that the mean is less than 10 pounds. So whenever you see these, you're going to notice these numbers are always the same. We want it to be the same because we want it to be the case that we assume this is true unless we have evidence that suggests it's not true, and then we automatically go here. So you don't want to have a gap. You want this to be 10, this to be 10. So we're going to believe that the mean is 10 pounds unless we see evidence to the contrary, and then we'll automatically go here and just say we believe the mean is less than 10 pounds. So that's what we've got. So just to make another picture here of what is going on here. So the claim is that this is a claim, the mean equals 10 pounds. And just think of this population as being thousands of numbers. Thousands of numbers. Each number represents the weight loss within the first month. And the claim is that the average of all these thousands of numbers is 10. So this group takes a sample out of here, a sample of size 36, and out of that sample, they get a mean of 9.2. Now again, we know that as we take samples out of here, even if this is true, it doesn't mean our samples are all going to be 10, right? And there's going to be variation in the samples. So the idea is, how far away can this get before we're ready to reject this? So that's what we're working on. And so we want to compute the sample test statistic, because we're basically going to figure out how likely are we to get this sample if this is really true. Or in other words, what's the probability of getting this sample if this is really true? So to compute the sample test statistic, or the z-score of that, we just use our formula we've been using quite a bit. And remember the things about this formula. Make sure you're careful about order of operations, and make sure you divide. It's a divide, right? So we plug in the numbers here. We have 9.2 minus 10. Remember, this mean mu is the one that's given in the null hypothesis. That's always going to be from the null hypothesis. And in 8.1, they're always going to give us sigma, which is 2.4. Divide it by the square root of n. N is 36. And just be careful to do this. And if you go through all that, we end up with kind of a nice answer, just -2. So we get an answer of -2, and because of what we know about z-scores, this does give us some information about how likely this is. This is a z-score of -2. So we know about how likely that is. It's a little low, right? 2 standard deviations below the mean, but not like impossibly small. It's not an outlier, but it's, it's a little bit low. So that gives us an idea of how likely this is, but we're going to go further than this. We're going to find the probability. So we're going to go a little bit further. One thing, though, I want to mention first is sometimes you'll see there'll be a study that comes out, and as an example, let's say this claim comes out in advertising. The claim is that the mean weight loss is 10 pounds, and you'll have a friend who says, you'll post it online somewhere, n equals 1, because it's your one friend, right? There's one person, and they'll say, that can't be. I went here and I only lost 2 pounds. So the average of 1 is 2 pounds. That's called anecdotal evidence. And in science, that counts for 0. So a sample of size 1 is a sample that should receive no weight at all. You really need to have more than just one person's opinion to sway science. Now, it doesn't stop people from saying that all the time. Some studies that are very thoroughly researched, they come out with a conclusion, and there's always somebody who says, that can't be true, that didn't happen for me. That's anecdotal evidence. In science, that counts exactly for 0. So once we have our sample test statistic, we have this z-score, now we can say, are the sample data compatible with the null hypothesis? In other words, is this compatible with this? Right? Is this okay? Should we expect this to happen if this is really true? So that's what we're going to look at here. This is really the key part of this problem. So we want to know the probability of obtaining a sample mean of 9.2 from a population with a true mean of 10. How do we compute this probability? Well, we use Chapter 6 techniques. You guys already know how to do this. We just haven't put it together like this yet, but here's what we do. We are going to figure out the probability of having a sample mean, less than or equal to 9.2. Remember, this is a continuous distribution, so you can just put less than also. It doesn't matter. Adding that 1 point with a continuous distribution doesn't change the probability. So what we're going to do then is change this to a z-score, which you've already done. We want to figure out the probability that z is less than or equal to -2. And this is what we'll always do. Just like before, we always want z-scores. So we always change x bar into z. That's what we did above. And then we know how to do this already, right? The probability that z is less than or equal to -2. Well, we did this all day long in chapter 6. To figure this out, we use normal CDF, -10, -2. Or you could use a table for some of you who missed the 1970s and love tables. Normal CDF is, again, typically much faster. And then from here, we'll get a number 0.0228. Okay, so this is stuff we've already seen. All this is chapter 6. But here's something that is going to be new for us. We have a new name for this. This number right here. Now we're going to call this the p-value. Now we haven't used that term before. So let me make a couple of pictures here so we can kind of see what we're talking about. So we have a normal distribution. Right, so we have this normal distribution with a mean of 10. And we've got 9.2 right here. This is a normal distribution. And this would be x bar. And that is this right here, right? The probability that x bar is less than or equal to 9.2 is this area right here. Now this right here is just this standardized. So we standardize that to get not just a normal distribution, but a standard normal distribution, where the mean becomes 0, and we are over here at -2. So this is a standard normal distribution. And we are to the left here because we want to know the probability that z is less than or equal to -2, so we're over here. And now we just found out this area under the curve, this shaded area for both of these is 0.0228. So we've got this new term here, p-value. We're calling this the p-value. Well, let me write down what the p-value is. So this is the area in the left tail, in this case. Sometimes it'll be the area in the right tail or even the area in both tails. But in this case, it's the area in the left tail because we're over here in the left tail, which it will always be when our null hypothesis is the mu is less than a number. Then we're going to be over in the left tail. So it's the area in the left tail that is equal to or more extreme, which means more to the left, so it's equal to or more extreme than x bar equals 9.2. Or in other words, z equals -2. And this area, the area in the left tail that is equal to or more extreme than this or this, is called the p-value of the test. Of which test? The hypothesis test. Just a p-value. So the p-value can be interpreted two ways. Number one, it's this area, right? This is just what we found here using chapter 6. We just never called it the p-value before. It's the area under the curve to the left of 9.2, which means at 9.2 or further, like more extreme. Like down here is going to be less than 9.2 pounds. right? So these are people who lost 5 pounds or 7 pounds or no pounds. That's going to be over here on the left. So the area, the p-value is the area in the left tail that is equal to or more extreme than this x bar of 9.2 or this z of -2. This area is called the p-value. But also p, another way you can interpret p stands for probability. So the p-value, that's a little messy, but probability, you can interpret it as the area under the curve or the probability. And the probability, when you think of the probability, it is the probability of getting that sample we got if the null hypothesis is really true. So, looking back here, we just found that the probability of us getting this sample, if this is really true, is actually pretty low, right? The p-value we got was 0.0228, or in other words, about 2.3%, right? 2.28%. So it's basically saying there's about a 2.3% chance of us getting this sample if this is really true. If the mean really is 10 pounds, we've got about a 2.3% chance of getting a sample like this. So that's the p-value, the probability. The probability of us getting this sample or a sample more extreme than this sample, if the null hypothesis is true, is 0.0228. So that's the p-value. We find it just like we did in chapter 6. In chapter 6, we thought of it as the area under the curve or the probability of getting the z-score here or to the left. But now we're going to just also interpret it in terms of the probability of getting that sample or a more extreme sample if the null hypothesis is really true. And down here they've got something that mentions it too. So the p-value, assuming h0 is true, the p-value is the probability, right? P stands for probability, that the test statistic will take on values as extreme or more extreme than the observed test statistic, computed from sample data, is called the p-value of the test. And here's what's going to be really important for us right here. This will be really important later. The smaller the p-value, the stronger the evidence against the null hypothesis. Because remember what that means. The p-value is the probability that we could get that sample if the null hypothesis is true. So if the p-value is really tiny, it's basically like saying the probability you would get that sample is like 1 in a million if that null hypothesis is actually true. And since we did get that sample, then probably that null hypothesis is not true. So that's what it is. And it's also can be interpreted as the area under the curve. So when we do a few examples, this will start to make a little sense. It might not yet. It's a little tricky at first, but when we do some examples, we talk more about the probability of getting that sample if the null hypothesis is true. It'll make more sense. So I'm going to stop this video at this point because it's getting kind of long and sometimes they're hard to upload. So I'm going to stop here and then continue this on section 8.1 part 2.